Okay, Cup, welcome to the I believe it's the 7th class of Big Data Analytics. Data Analytics for data set, whether or not we're talking about big data or structured data. So let's look at, let me go to the syllabus, right? Okay, where are we? Well, we are kind of right here. We kind of about here. So we are about here. Okay, supervised learning. Okay. Now, in the beginning, we focus quite a bit on what to do with data, how to visualize it, and so forth, right? And talk about this, and we even went back to review. I guess what would be your first lessons in data analytics, which is to analyze data using probability model. Okay, so you have a probabilistic model or probabilistic assumption about how your data is distributed, and then using real data, you fit the parameter of that probability distribution, and that's that's the statistical method. That's how you fit the real data or empirical data. Okay, so that would be I guess the first type of data analytics that you are used to. Okay, in fact, it's taught in freshman year in just about every program. Okay, now because we are dealing with a more general case that is not necessarily numerical in nature, and also even if it's numerical, it may not have a very nice probability distribution. It may not look like the usual normal distribution or binomial distribution. So we have to kind of generalize the method to something that is not handled within classical statistics. Okay, so that's why here, right, when we talk about data analytics, we talk about statistical methods and machine learning methods. Okay, we are by design in this class going to be focusing technique-wise on the machine learning, because we are assuming that the statistical method we have studied at least introduction or freshman or year 1 class in probability and statistics. Okay, so if you look at the syllabus, we are making a shift, right? We're shifting gear a little bit, whereas the last week or so we were dealing with what we call unsupervised learning. Now we're shifting gear. We're moving to the space of supervised learning. Let me say this. Okay, if you think about it, the first thing we tackle is visualization. Second thing we tackle is unsupervised learning. Third thing we tackle, not counting the review. Okay, forget the review. In terms of the subject, we start with data visualization, and we have unsupervised learning, and now we go to supervised learning. I would like you to think of it this way. Data visualization, like I said, is a form of analysis, because sometimes when you visualize, you get some insight right away. Okay, but like I said before, data visualization is a tool. It's used by analysts. So as you're doing the machine learning, you're doing all kind of advanced model. Before you do that, you want to visualize your data. As you are doing it, you want to visualize how your data gets fit. And at the end of the analysis, when you get the results, you're going to get all kinds of accuracy or error or some kind of performance measurement. And you want to see, how the data is actually fitted and what kind of error are we getting. And if you get the right insight, what kind of relationship are we getting? So you get back to visualization again. So you can say that visualization is the beginning but you're going to be using it throughout. Well, a little bit in the same vein, even though unsupervised learning and supervised learning can be thought of as two different subjects. In real life, even when you're doing largely what's called supervised learning problem, the problem looks like a supervised learning, and we'll talk about it in detail. Chances are throughout the process, like the beginning part where you do some kind of data exploration or something like that, or maybe the end of the project when you're trying to visualize the insight, you might use unsupervised learning techniques. Okay, so if we say visualization is 1, unsupervised learning 2, and supervised learning 3, I'm going to say that visualization is used everywhere, okay, for its own sake and as well as for machine learning. And when you go to machine learning, some task is about unsupervised learning, some task is about supervised learning. But even when you're doing supervised learning, chances are in the real project, you might have to start with some kind of unsupervised learning, some kind of get the right picture of how data are distributed and clustered and so forth. Okay, so that's why unsupervised learning comes before supervised learning. Now, having said all that, I can also say that professionally, data visualization will be done in a sort of like business intelligence kind of unit. So not really data scientists, people who build dashboard and stuff like that. So a proper data visualization is usually performed by guys who are, maybe using Power BI or Tableau or some kind of visualization tool, but not really data scientists. Okay. Professionally, data scientists start to make their value, their contribution in projects that require supervised learning and unsupervised learning method. Okay. And between those two, I can say that, I guess from experience as well as from survey, right now, majority of the application or of the project will be based largely on supervised learning. So supervised learning is really the one tools the sort of approach that you would see driving most of the data science project. Again, bear in mind that while you're doing supervised learning, you might have to do something like unsupervised learning alongside, and certainly you have to do visualization throughout. Okay, but as a name of a project, as a project name, as a job that you get hired to do, or consultancy that you're asked to solve a problem, supervised learning is really a big chunk of data science, a very big chunk. Okay, it's a very big chunk. So let's talk about supervised learning. Now, before I talk about supervised learning, okay, let me just go back one more time about statistical method. You would notice that in your probability or statistics method class, right? A majority, say first half of the class, you study about probability models. So this gives you a way of constructing the shape of the distribution. Once you get the data, you do the estimation, where's the mean, where's the variance, and trying to fit, okay? So that is a sort of statistical method. But I don't know if you had this, but in most statistical method class, toward the very end, instead of just fitting distribution, you start to do something called linear regression. Now, the feeling is different. With distribution, you're talking about, where is the population, where are the values? Whereas with regression, you start to have two sides or two camps, right? One variable or one set of values is what's called predictor, and the other set of values are called predicted. In other words, they don't have the same status. You have information on one set of values, but you try to make a model so you can predict or estimate or guess or forecast the values of the other thing. Okay, so loosely speaking, if you're talking about distribution, you're trying to find the distribution of X. But if you're talking about regression analysis, you are given X. You're trying to predict Y as a function of X. Okay, so keep that in mind. Those are two styles of analysis that you had, presumably, in your statistics class. Now let's go to supervised and unsupervised learning. Well, you would see that unsupervised learning has a flavor, like we did last time, very similar in feel to statistical method. You're just trying to get a data and you're trying to find out where it is, except you're not trying to fit the probability model. You're trying to find out where the clusters are, for example. Okay? Supervised learning will have the feel of a regression analysis. Okay? Will have the feel of regression analysis where you have the data set, okay, basically the values, but you separate certain sets of values, a collection of values, okay, as X. And then you designate something else, some other value field as Y. And you're not trying to find how they are distributed together. You're trying to say, if I were given information on X first, can I guess Y? And what's the best way, what's the best method to guess Y given knowledge of X? So there's sort of like an arrow from X to Y. And that's the realm we are going into. So that's where we're shifting here. Okay, so let's look at this. Now, to summarize, and I want you to follow this line of reasoning, right? So you can see the share. Okay, so we talk about model, yeah, and I think I did this in the first class, right? And sort of like quantitative modeling. There's optimal control models, you know, like things like controlling your robots and so forth. There's optimization model. Remember, I told you that in life, instead of having a unique solution, you tend to have more than one solution. You can have infinitely many solutions, but you're trying to select amongst the best. Which one is the best? So that's sort of like optimization model. Now, we are talking about system model. So let's go, okay? So what makes a good system model? Well, it has to be, you know, realistic and so forth, okay? But I'm going to follow this. Let me make it a little bit bigger. Okay. So what are we trying to model? Okay. What are we trying to achieve when we talk about system model? Well, we're trying to do two things. We're trying to gain some kind of insight, or we kind of solve some kind of problem. Okay. So solving a problem is like model inversion. Okay. So which X would give you a particular Y? Now, this would be something like solution solving. Okay? That doesn't happen. You don't get a lot of this kind of question or this kind of project in data science. What you will get a lot is this model building. You build a model to represent reality. And now this is where I separate into two types of model. There's a model that say, where are the X's? Where are the X's? And there are the models that say, if I knew X first, what can I say about Y? Now, perfectly would be something like, if I knew X, I can predict the precise value of Y. Okay, given X, I can tell you Y exactly. That'd be like a perfect prediction. But that doesn't happen. Sometimes you just have a more rough statement about Y, like, well, what's the probability that Y will take on this certain value? Or, you know, estimate value of Y with certain degree of confidence. Okay, so it's not going to be precise. So again, where are the X's? Okay, where are the X's in the world of statistical method? That would be like distribution analysis, right? That's what we did before, right? Mostly, therefore, you would use statistical method, mostly. Okay, if you're trying to find out where the distribution, you mostly use statistical method. And we saw, you know, the powerful mathematical way of trying to find distribution and so forth. Rarely do you use machine learning. And this is I'm giving you this, like, well, it's not just from my experience. This is really by in reality, in industry, in practice. Okay, most of the time, if you're trying to find where the data is, you're trying to find the distribution, you use statistical method. Rarely do you go straight to machine learning. There are some special cases where you do what's called data mining, and we saw example of that last class, right? Last class or the class previous to that, we talked about basket analysis, right? Things like, for example, let me write that example. For example, oops. For example, market, basket, frequent item set, okay, analysis, okay, right, and so forth. Maybe there's some other thing. Okay, right. So now today, okay, and we saw cluster analysis again. Occasionally, it's the flip side. Occasionally, cluster analysis will be done using statistical method, but most of the time, generally speaking, we talk about machine learning. In particular, oops, in particular, unsupervised. Okay. Now, so today we're shifting gear, and we're now interested in this kind of directional inference. Okay, this one keeps showing up. If I knew X, what can I say about Y? Well, if Y, okay, if Y is quantitative, okay, or numerical, you guys remember that? There are what kind of rate, what kind of scale? By the way, I like to ask this simple question in the exam because it's simple, and yet most of you guys will forget. Okay, what kind of scales are we talking about? We're talking about quantitative, numerical values. Okay, obviously, interval and ratio scale, right? Well, when you do this, the problem is called regression analysis. Okay, we'll just call it that. We'll just call it that. Yeah, I'll tell you what's the reason for the name later. Okay. Now, if Y is descriptive or categorical, okay, what kind of scale are we talking about? There are two more scales, right? The number scale. Okay, what kind of scale would Y belong to? Well, it can belong to nominal, or it can belong to ordinal scale. Okay, well, if Y is kind of descriptive or categorical, okay, so if Y is quantitative, it would be something like, if I knew X is the weight of a person, can I guess the height of a person in centimeters? So that's numbers, right? Whereas if I knew X, what can I say about Y? But Y is categorical. It would be something like, if I knew the height of a person, can I guess if it's going to be a boy or a girl? Okay, obviously that's not a good question to ask, but certainly you can ask that. Then Y is descriptive or categorical, because you can be boy or you can be girl, something like that, right? And that's called classification analysis. Okay, so you have two things. Now, regression analysis, traditionally, okay, now I'm not saying more or less. Now I'm saying traditionally, meaning that before you were born, this would have been done using statistical method. But more and more, you use machine learning. In particular, supervised. Okay. Classification analysis. Now, what do you think happened? Oops. Classification analysis, once the norm is statistical method, just like before. Okay. Primarily now, machine learning. Now. Primarily now. Now primarily. Primarily with machine learning. Again, This would be supervised learning. In special case, you also do data mining. Okay. Now, whereas this you would do something like a frequent item set. Here you do something like frequent sequence, for example. Okay. Now, why would you say what's the difference? Frequent item set would be something like what kind of basket happens a lot, like milk, bread, and butter, and so forth. Sequence would be something like given that the person bought milk and bread in week 1, is he likely to come back in the 2nd week or the 3rd week to buy something else? Okay, so it's kind of X to Y. So that's okay. So that's it. That's what we're talking about. So now we are going into this bit, machine learning, in particular, supervised learning. Okay, so let me flip to the other side. Flip to the other side of this. Post the introduction. We give you an overview. So this is a map. Statistical method, we're going to ignore that because we've learned that already. Now, this is the thing I want to let's post it a little bit. Okay, in machine learning, there are many aspects. Okay, now if I ask you on an exam, for example, what are the 3 basic or major category or paradigms of machine learning? Okay, obviously your answer would be 3, right? Remember, just like baby learns, right? Baby learns in an unsupervised manner, baby learn in a supervised manner, right? And then you, as you go through life, you learn through reinforcement learning. You get reinforced. Good behavior gets positively reinforced. Bad behavior gets negatively reinforced. So in terms of machine learning paradigm, right? You always say there are 3. I guess this is convention. Okay, convention is you separate machine learning into unsupervised, supervised, reinforcement learning. And I made the point early on, I think in class 1, that even though machine learning has these 3 major parts, in data analytics, you are not going to use reinforcement learning very much. So I'm leaving that entirely out of this class. So it's not in the syllabus. Okay, but certainly unsupervised learning and supervised learning are fair games. Now, my separation here, okay, is about the sort of things you learn. Okay, the sort of mode of learning. So what you get when you learn. Let's put it that way. Okay, you get rule learning. So this is close to what you will see with reinforcement learning. You learn what the right rule is. This will be probabilistic learning, meaning you learn what the probability is. So you can think of it as a modern approach to doing statistics, right? Whereas back then you make the probability model assumption, you get the data, you fit the statistics, and you say, okay, that's my statistical estimate. Now you try to get probabilistic statement without making that assumption. So it's a machine learning way of doing probability model. Okay. This thing is a little bit more difficult. It's saying that you're learning how the data itself. Okay? So this is sort of like a generalized version of cluster analysis, right? Data is called manifold learning. Okay, this term is not universal, but you're trying to learn how data gets distributed in higher and higher dimensions. Okay, and then there is this thing called neural learning. That means you learn, but what you learn gets crystallized or gets packaged as some sort of neural function, or an algorithm that behaves like a human brain. Well, it doesn't have to be human brain, but biological neural network. Okay, and then there's this thing called ensemble learning. This would be something like you get all kind of information from here and there and here and there. We're trying to pull the information together. So this is kind of like community learning, if you will. You know, one person may learn by this technique, the other person may learn by that technique, and as you create an ensemble of experts, maybe you do some kind of voting, right? Maybe one person use econometrics, one person use neural network, the other person use data mining, and you have three of them. They all give slightly different answer, and you sort of like trying to get the final committee approved, so to speak, solution. So that was kind of ensemble learning. Finally, there's this thing called evolutionary learning. This is a very advanced topic, like it falls under evolutionary algorithm. So basically, my thesis and a lot of research in people near my area focus on that. Okay. As with reinforcement learning, this is not that dominant in data analytics, in playing with data. It's good for something else. Like if I want to learn about an algorithm, right? You can evolve the algorithm to trade currency or to trade FX or something like that. In fact, my PhD thesis was about evolution of algorithm or evolution of algorithmic trading functions or programs. So we are going to go into this thing. Yeah, I'm gonna skip the line. I don't forget about this guy. So there's gonna be basically supervised and unsupervised learning proper. So this is what we have. Okay, I'm gonna forget this guy. This is one. So unsupervised learning. Okay, and so many things. Okay, there's plenty more. There's today we can talk about supervised learning. Now, supervised learning, supervised machine learning. I'm going to touch on a little bit on what's called embedding. Okay, but basically we're going to deal with classification and regression. Okay, classification and regression, and all of this. Okay, both classification. There's also tree-based method. For example, decision tree. Okay, and forest, gradient, boosted tree. Okay. Yeah, something like that. So this are sort of like the tools that you'll be learning. This one later in the class. This one we'll learn today or next class. This one may be the class afterward. Okay. So classification. Likewise, regression. We'll also learn that. This one might be sort of like later on in class. Okay. You can also have tree-based here as well. Yeah. So that's the sort of thing we are going to learn. But today, okay, I'm gonna focus again on very basic neural learning. Okay, so that's where we're heading. Okay. Let me actually I don't think I need this anymore. Okay. So once again, let me bring you back to what you learned before. Okay, what you learned before. What did you learn before, right? In regression analysis? This is an artificial problem I just made up. Okay, an artificial problem. You will notice. Okay, well, this is too many things. Let me start here. So this is the noise. Okay, this is the noise. This is sort of like randomness. Okay, if I have this, all I have are this bunch of points like this. What would you do? You try to fit some kind of distribution. Okay, I can tell you right now, this is called a uniform distribution. So the first data point, second, third, fourth, everything is evenly spread out between -10. Let me make it a bit larger. So, okay. Right now, you don't have to model this because I generated this data using this thing called random real. Okay, it's a table of random real between x min and x min plus range. So x min is say -10 and range is 20. So -10 to -10 plus 20. So that's -10 to plus 10, right? And the number of data, I set it equal to 100. And I just make a list plot, right? So that's that. That's that, right? So let's make a 1,000. Okay, so it's a lot more. Now, basically, if this were statistical method, okay, you would do some kind of histogram and then you would try to say, well, it looks like a uniform distribution. And if it's a uniform distribution, you can only specify the range, and hopefully you come up to the right conclusion that it's uniformly distributed between -10 and 10. So this is just something completely random. Okay, so I can do something else. Okay. Anyway. So that's some kind of noise. Okay, that's some kind of noise. Now notice this is not even uniform noise. No, sorry, this is uniform. This is not even Gaussian noise. I can also make a Gaussian noise, right? But, so I can make a Gaussian noise. So for example, let's make let's do another one. Okay, X data number 2 is table random variate of normal distribution of mean 5 and standard deviation 2, say, okay. And I'm going to get about in data, so about 1,000. Okay, so that now I'm just going to go ahead and list plot this thing. This plot table. Okay. See, so this one, by the way, you will notice that it's sort of like thicker, denser around the value here. So that's 5. And so if you plot the histogram of this guy instead, yeah, you get something that looks like this, right? So this again is what you would do if you make an assumption. It's a normal distribution. You say, oh, where's the mean versus standard deviation? Okay. Now I'm going to create a different set. Okay, I use normal distribution too, just like before. Okay, just like before. Okay, in fact, I did that already. But now I'm going to create X and Y pair. Okay, X and Y pair. So now I'm going to say that, okay, by my own construction, right? X going from whatever -10 to plus, it doesn't matter. But Y is going to be equal to something called beta 1 plus beta 2 times X. So that's a linear function, right? Plus some kind of noise. Okay. Now I made this data set up. Okay. In reality, you would see something like this in real life, and you're trying to find what the intercept is and what the slope is. That is the essence of what? The essence of linear regression, right? Linear regression is to find the fit and the slope such that you fit this data set. Now, let's say you didn't do a good job. You did a poor job, okay? You did a poor job. Now, remember, what I did was intercept is 5, the slope is 1, okay? Now, let's say you did a poor job. You made, so this will be something like nature. Okay, this is hidden from you, by the way. You don't see this. This is nature's number. Yeah, it generates this number. So you don't know this. So you make a guess. I make a guess that the intercept is is only half. So in other words, my guess is off by half. Okay, let's say my guess is off by half. Okay, I almost get it, but I guess too small for both values. What's going to happen? So what I'm going to do is I'm going to show. So you can see that show is a function that basically show a few things on top of each other. You see that, right? So show. I can just keep adding things to show. I show the first thing is the list plot of this thing. Second thing, I plot the line. But certainly I did a poor job, right? Remember that? The true intercept is 5. I guess 2.5. The real slope is 1. I happen to guess a half. So that's a bad thing. That's a bad thing, right? So I'm not getting the right. I'm not getting the right fit. So what's a better fit? Well, the way to do it is to think of the error between given x. This is what I predict. This is real. This is what I predict. This is real. And just add the error. Add all the error. Okay. And that's what this is. Okay. So root means, so I take residual is equal to the fit and the data, or data minus fit. Okay. And I take a root mean square. You know what that is, right? So you take the you take root mean square. Looks like this. Root mean square A, B, C. Okay, so A squared plus B squared plus C squared, right? Divide by 3 and then take square root. Okay. So what I'm doing here is my error. Now I just make a nice little thing called root mean square error as an angular gauge. You just basically compare it. Now, this RMSE, this is the real noise that I use up here somewhere. Generate the noise, okay? There, see? Okay. So this is the real noise of the real root mean square of the noise, okay? But this is the root mean square of my fit. So obviously, there's a difference, okay? There's a difference. It's not quite right. In other words, this is the real noise. This is the amount of noise I have. This is the amount of noise my line fit has. Okay? So now I want you to think of it this way. Now again, some of you may have done linear regression until you do generalized linear regression, but I'm actually going to dissect individual itsy bitsy piece of linear regression, because we are going to generalize that. Okay, so basically, now if you think of this distance, right? This distance, this error, okay? There's a minimum error, and there's the error that my guess is. So if I guess right, let's say if I guess right, yeah, I just happen to guess right. Okay, I'm cheating here. I happen to guess right. There, I get perfect. This is as good as it gets. What happens here? The error, right? So the error from your model, which is the blue one, is exactly as low as it gets. Now, if I make it even worse, 7.2. Okay? Terrible, very bad. Okay, let's look at the error. Terrible, right? Very far off. Okay, so let's go back to the original. So was it 0.5 and then 0.5, so not too much, and maybe 2. Okay, so that's still not good. Okay, now you can imagine, right, that this is a value of the error. You want to get to be as low as is possible, but it can get far away, arbitrarily far. It depends on the value you chose. Since there are 2 values, these are the parameter, I can make the plot out of it, right? So this is the list plot 3D. You can look at this in detail, okay? But basically, what I did was I make one axis to be the value that I guess for the intercept. The other value I guess for the slope. Now the right value is here, and this is the error. So the right value is here, okay? So the right value is this. Okay, but say it's here somewhere. Okay, if I guess wrong, every time I guess wrong, whether or not I guess wrong with respect to the slope or the intercept, my error gets bigger. Okay, my error gets bigger. Now, just to emphasize, I draw this line, and this is I just want to show you that this is how the lines are drawn. This is the line from your prediction and actual, right? So this function here that I create, by the way, okay, this here, which I deploy on cloud. Remember that? If you go to this thing, I put that in the line. If you click this, you will get just this, just this thing. You don't get the thing above. But the point is this. Okay, what are we talking about here? What are we talking about here? Let's make it smaller so it fits in here. Smaller still. Okay. Oops. Smaller, not larger. There. Okay. You can imagine that this is the game you play. You're trying to draw a line, and you're trying to take the difference between the actual value and the lines. And that's the height of error. You take square of each value, square plus 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 square, divide by the number of data points, maybe 100 in this case, okay? And then take the square root. And that is the value here, the blue value. Okay, that's the error. Now, there's some inherent, even if you get the perfect fit, there's going to be some remaining noise that you can't get rid of. That's the baseline error. That's the rate. You're trying to get the blue to go down to red as much as you can. And it is possible. You can make it worse, you can make it better. How do you make it better or worse? Depends on the value of the beta. And those are the two values here. So what I have done here is to say, I have this data set. I want to turn this into a regression problem. Regression problems say, if I knew X, what's the best guess for the value of Y? Okay, if I knew X, what's the best guess for the value of Y? If I guess it right, this collection of black lines here, square, average, and square root will be as small as it gets. So the name of the game of linear regression is to play with the intercept and the slope, which I call beta 1 and beta 2. Play around so that I get to here. So I have turned a problem of creating a model, the model to predict Y given X, into a problem of fitting a line and measuring the error, and then selecting the line parameter in such a way as to minimize the error. That's what you did when you did linear regression. However, this problem of linear regression is 300 years. So again, you did linear regression. Okay? When you learn linear regression, you're actually given the formula. Okay? You don't have to find beta 1 and beta 2 or slope and intercept. If you are given this set of data, there is a formula that's given to you for calculating the best intercept and the best slope. Okay? That's because this problem has already been solved. It's already been done 300 years ago. Okay? But I'm going to take the step apart, right? Instead of getting the right beta 1 and beta 2 right away, beta 1 again is the intercept, beta 2 is the slope. I want you to think of this problem before the formula came out. The idea is you want to create a model that gives you the best guess for the value of y. That's the vertical axis, given the value of x. So if I give you the value of x is equal to 5, the model should give you the value of y that is close to the real data as possible. Okay, so it should be around here. If I give you a value of x is equal to -5, your y estimate should be near 0. It should be around here. The point is, what is your model? Your model comes in the form of y prediction is equal to intercept plus the slope times x. Except you don't know what the intercept and the slope is. The way it's done behind the scene is that as you change the slope and intercept, by the way, I make this a two-dimensional thing so I can move it together, okay? So I'm moving just the beta, not just beta 1, but beta 1 and beta 2 at the same time. I keep moving. Let's say I'm moving randomly. The line, black line here, is the error. So I turn the function of create the task of creating the equation that best fits the data, which is actually the model for predicting y given x, is turned into a different task. That task is to find the intercept and the slope of the line that minimize all this error. Okay, and you only have 2 degrees of freedom. You have 2 parameters. You can play with 2 things. There's only 2 things you can play with. 1, the slope. 2, the intercept. Okay. Now, if I, for some real lucky reason, I make the right guess. Yeah, I make the right guess. Yeah, make the right guess. For some reason, I make a very good guess. Not quite. There. That's my best guess. Let's say this guess. Oops. Okay. Move a little bit. Oh, come on. Okay. Is this the one? Or a little bit to the right? Oh, too far. Okay. There. Okay. You would see that all the black line here, square, average of that, take square root, is small. So this now is on top. Maybe not quite. I have to move it a little bit more. Okay. So that is what's called supervised learning. Wait a minute. What do I mean by supervised learning? The supervised learning, this now, I give you this. The reason it's called supervised learning. Okay, so let me draw a little class note as I usually do. Note. Okay. In, let's say, recall. Let's make it bigger. Recall that in linear regression, okay, given x and y data, okay, you want to find y estimate equal to, say, a plus b times x. Okay, and so you get a formula for a and b, right? And then you're done. Okay, and that's called linear regression. Now I'm going to make life more difficult. I'm going to say I'm given x, y data. So let's call it x sub I, y sub I equal to 1, n. Okay, given the same data, okay. right? Now, guess A and B. Guess A and B, okay? Guess A and B, okay? And then Y guess, Y estimate at a given guess is equal to A guess plus B guess X, right? Now, so Y guess is equal to A guess plus B guess. How does this work? Well, you just get a whole bunch of Y I guess. Okay, and then you get is equal to A guess plus B guess. Okay, oops. A guess plus B guess X sub I. A whole bunch of them. And okay, and then you say, what's my error? It's equal to root mean square of Y I guess versus Y I real. That's my error. It turns out this error is a function of your data, obviously, and a guess. You can't change your data, but you can change your guess. Okay. Now, this error function is this thing you see here. And you want to minimize this thing. By changing A guess and B guess. Okay, so this, why do I say that this is a supervised learning problem? Why is it a supervised learning? As a supervised learning problem, okay, we do this. Why is it a supervised learning task? Why? Task. Why? Remember, supervised learning task, you pick an object, you pick an apple, you tell your mom, apple. Your mom say, good. You pick an apple, you say, orange. Your mom says, bad. Right? In fact, it is orange. It's not apple, right? So it's bad. Why is this a learning task? Because based on your guess. Oops. Based on your guess, and based on your guess, now you're not guessing this, you're actually guessing why, right? Based on your guess, actually implicitly you're guessing this, okay? But based on your guess, you are told right away whether you are right. Right? And how do you tell what is the rightness or wrongness? Well, that rightness or wrongness is this, right? Right? Now, because I want to have no error, it doesn't matter if I guess too big or guess too small. So I'm going to put absolute value around it. So this amount of error, this is amount of error. So when you pick up an apple and you say orange, your mom say wrong. You guess again, and then you say apple. Well, in this case, when you guess again, yeah, new guess. Guess again. Yeah. What you want to do is to improve on it. So in other words, this is your error, right? Now, this is error on individual. So I'm going to put some so that it's not just apple and orange, but you know, bananas, all kind of example. Okay. So forget this I equal to 1 to the n. Okay. I'm just going to just write this in bracket. Based on this guess, you want the new one so that this thing, yeah, is much less or less than this thing. Guess again, right? We guess again is less than all guess before. Okay, so you do this, and how many times do you do this? You do this until you stop, until you get all the answer as close as you can get. Okay, so how do you check guess again? i.e. by moving A guess and B guess. So this is your supervised learning task. Okay. Now, 300 years ago, somebody already did this for you and gave you a formula. Okay. But I'm going to ask you to do again without the formula. Okay. But you have an algorithm. An algorithm is to say, start with some guess, measure the error, and then guess again, so that the sum of a whole bunch of error is less than with the previous A guess and B guess. Okay. And when you get the finish, end up with A best guess and B best guess. Okay. So that's it. That's the problem. So this A best guess and B best guess is this formula for this. Okay. But now you're done. Okay. So why would I undo 300 years ago what was done for you? Because what was done for you only works for this case. It doesn't work for a general case. Now, you can still play around with it. For example, I can do this. Say fit a parabolic, right? So I can still do the same game. Now, this one I actually don't have any noise. There. See? Similar thing, right? Well, in this case, it's not that fancy. It's just saying the equation is parabola. Okay? So the y, so in this case, it's like before, except something like this is x to the power 2 or something like that. Okay? So as long as you have the function, if you have, so you have to under the assumption of, okay, A plus B x, y is equal to A plus bx, plus say normal noise. Under this assumption, you can do this. Under the assumption this. Okay, so under assumption of this, you can also do, right? So you can do a few things. Okay, you not just fit to linear. So what you can do is non-linear regression. Yeah, so maybe you get something else. So maybe this is cubic function, right? You get perfect. You know, the same thing, right? So this is the error function. You try to get so that the blue is on top of this as much as you can, as close as you can. Okay, so that's the name of the game. Now you can think. Okay? Think of error function as a value. Okay, you know what a value is, right? So let's look at the picture. So picture of there. See, looks like that, right? Right? So think of this picture. It's not much different from this picture, except this picture is the height in elevation, but I consider this height error. So I want to go down as much as possible. So you can imagine that my initial guess puts me here. I want to keep going, maybe small step at a time until I get here. So you can imagine that you start here, right? And you look at your error, and it turns out that you can improve. You can do things, you can do better. You can do better, right? Why? How do you know you can do better? Because you're standing at a slope. So you notice that, hey, wait a minute, you're standing at a slope. So actually, you're not at the bottom. So let's move down in the direction, okay, of the slope. Go down, go down, go down. Just descending, 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 descending. Okay? Now, you know what? You can descend here, you can descend here. You can slowly descend if you go like this. Okay? Now, you want to go into the descending direction of the greatest slope. Slope in topography or in map making, I don't know if you guys have been to Boy Scout. They don't call the slope of the mountain. What do they call it? Anybody been a Boy Scout, Girl Scout? Mountains. They don't say slope. What do they say? Gradient, right? So basically, it makes sense. If you want to go down as fast as possible, okay, you don't want to take your time. You want to go down as fast as possible. You want to descend in the direction of the steepest slope or the direction of steepest gradient. Or what you want to do is follow a gradient descent instruction. Now, human beings follow instruction. Computers don't follow instruction. Computer follows algorithm. So I'm going to write this down. Going down the error function, okay, in the direction of greatest slope. Okay? You want to be going down. Okay, so going down is an instruction for human, i.e. algorithm for computers. Okay, down gradient. Okay. Down is descent. Okay. Steep gradient, slope, gradient. Okay. So you want to be going down in the direction. Okay, so I put all this together. You get, okay, you get, in other words, you tell the computer to follow gradient descent of the. Okay, that's what you want to do. That's a general principle. So again, you already know how to do regression. I just make the problem that's so simple, very difficult, so that you can follow the steps. This is a general process. You want to follow this. So look at this picture here. Okay? Okay? You want to go down, descending in the steepest direction. Now, obviously, there are many other ways, right? For example, instead of you right here, right? You going down here and say, where is that value? You can actually just parachute 1,000 people. Okay? You parachute 1,000 people. One here, one lands 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 here. And everybody has a radio communication, right? Like a walkie-talkie. And everybody looks at the watch, the altimeter, and say how high that person is. So this person say he's 2,000 feet above seawater. This one say, oh, he's only 1,000 feet above seawater. This guy turns out to be 50 feet above seawater. And nobody is lower than that. Nobody is lower than that. And move around a little bit and nobody gets lower. So that's also a way of finding the solution. Okay? And that's called random search. Okay? But this way, it's called gradient descent. So that's what you want to be doing. Okay? That's the name of the game. So name. So the name of the game is in supervised machine learning. Supervised machine learning instead of assuming y is equal to a plus bx plus noise. Okay, you don't make any assumption. Well, you make a little bit. You just create a class of function f of x. F of x given parameter, say beta. Okay, so instead of a and b, okay, you do this. That's it. You create a class of function, okay, and then you find the beta that minimize what? F x of I given beta versus y. This thing is blocking. That's it. Can somebody help me stop this thing from? That's it. That's the name of the game. Okay, that's the name of the game. So why did I throw away the nice formula that was discovered 300 years ago? Because the formula that works 300 years ago only worked for something that looks a little bit like that. Okay, maybe fancier, more polynomial. So this thing, by the way, is called linear regression. But if you have something like x to the power 2, it's called polynomial regression. Okay, but still, you know, it's very limited. Here it's more general. Okay, so an entire class. Okay. Now, in practical term, okay, in practical term, you have many F. F1, okay, I'm gonna forget X now. Okay. F1 given beta 1, right? So that could be F M given beta M. Okay. In particular, in this class, your F may be something like neural network given beta of neural network. Yeah, so I'm going to call it NN. Okay. Okay. And you have something like, what else? You can have, well, what about decision tree? Given beta decision tree, right? This is what you learn in class. In practical terms, you will learn. Now, what happens in practice? So that when you see X, I, Y, I, in real life, you choose from the above set, for example, we choose NN, and find beta NN using gradient descent or something else. Most likely using, okay? There are many other things. So that's it. That's it. I don't know if this is as clear. This is basically the best way I have found, you know, over the years to introduce the concept of supervised machine learning. It's like you are doing regression, but with regression you come with a pre-packaged assumption. You make this kind of assumption. Okay, maybe you can assume something else, but not much, not much. And based on that, because you know it's simple, somebody 300 years ago came up with the formula. Okay, and that's why you have, if you go to let's go to internet, you can go something like OLS estimate for linear regression equation, right? It's given by, there should be a Wikipedia page actually. Okay. If you make the assumption like this, okay, right? Beta, start with beta 0, not beta 1. But anyway, it's the same kind of thing. Blah 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 blah. You end up with fit. Okay. Now, that's exactly what I want to show you. Now then, okay. So that's it. That's the gist of this.